Hey there, everybody. I want to take a few minutes and go over the homework problems that we finished on Thursday. I just point out that I've got my nice new I Love WKU Math shirt on. Okay, problem 6. If there are 8 enlisted ranks in the country's army and 36,001 enlistees serving, what can we say about the number of enlistees at each rank? Okay, well, this is straightforward pigeonhole principle. It's the generalized pigeonhole principle, correct? So we can say this: there are at least we take the ceiling of 36,001 divided by 8. That is roughly 50 and a half, 50.5. And so when we take the ceiling of that, that is 51. Wait, I'm looking at the wrong number. Excuse me, I don't say that's not, there's no way that could be right. That is not right. I will just act like that never happened. Excuse me. I'm looking at the wrong problem. Pretend that never happened. Because that's divisible by 8. So whatever that is, I think it's just a smidgen over 4,500. So this is 4,501. There are at least this many enlistees serving at the same rank, or at least one of the ranks. Okay. And let's see, 7. A wildlife photographer has placed motion-activated cameras on 6 game trails. Each camera is loaded with 24 exposure film. How many game crossings would guarantee that one of the 6 cameras had 24 exposures? So what you could do here, right, is for each of the 6 cameras, the worst case scenario would be, well, we end up with 23 pictures on each of the 6 cameras, and then we add the 1. So I believe this is like 138 plus the 1 would be 139 game crossings. And if you check 139 divided by 6, if you take the ceiling of that, that will give you 24. Okay, 132 divided by 6 is actually 23, and so the ceiling of that would be 23. But this is the first one where you get 24. Alright. Now to the problem I was looking at earlier. University has 8,500 students. More of them have a birthday on August 29th than any other day of the year. What is the minimum number of students with birthday August 29th? So, and this is in a way a straightforward kind of generalized pigeonhole principle problem. We've got 18,500 divided by, and if we count February 29th as a birthday, then there's 366 birthdays possible. And so this is roughly, and this is what I was looking at earlier, about 50.5. You take the ceiling of that, it's 51. Then there would need to be, so what we're saying here is that there's at least 51 birthdays on the same day. But that could happen on multiple days. To say that we have more on the 29th than any other day, we have to say that there are at least 52, see, and folks in class were good to point this out, more of them on than any other day. birthdays on August 29th. Okay? Alright, problem 9. 50 ping pong balls numbered 1 through 50 are placed in a vat. How many balls must be drawn to ensure? And part A says a pair whose sum is 50. Alright, now, there are only certain pairs that give me 50. Right? 1 and 49 would give me 50. 2 and 48. However, 25 cannot be paired with anything to get 50 because I need two 25s and I don't have them. And also 50 can't be paired with 50 or with 0 because there is no 0 there. So there are 24 pairs that sum, oops, can't spell, 2, excuse me, and 2 singles. That would be 25 and 50. Okay? Thus, if I want to get at least, get the minimum number of balls that I have to draw to ensure that I get a pair, okay, first I've got to get these, let's say I get those singles, I draw those first, right? And then with 24 pairs, I need at least 25 to make sure that I've got 2 in one of those pairs, right? So that's 27. Then to get 2 pairs summing to 50, well, it's the same problem. The previous 27 plus 1 more. I can't have repeats, so that's 28. Okay. A pair whose sum is 75. Okay, by my count, there are 13 pairs that sum to 75. You can start with 25 and add it to 50. 26 and 49, all the way down to 37 and 38. Okay? Plus, and that's 26 of those things, that means there's 24 singles that do not. Okay? Thus, worst case scenario, I'd have to have those 24 and then 14 others, right? 13 plus 1. So I think that works out to be 38. Okay? And then a pair whose sum is 99, there's only one pair that adds to 99, and that pair is 49 and 50. So we'd have to get all the other 48 and then those 2, which means all of them. Okay? Alright. 10 was probably one of the more challenging ones, although it's a variation of one that was given to you in the examples in the chapter. It asks us to show that any set of 50 whole numbers contains 2 non-empty disjoint subsets B and C, such that the sum of the elements of B and the sum of the elements of C are each multiples of 25. Okay? Things that are important here, you've got to be disjoint subsets. The way we guarantee that is go ahead and split this up into 2 disjoint subsets. So let A1 equal be a subset of A, and A2, I guess I should have defined that these things are in A, the ends, N26 through N50, subset of A, where A is N1 through N50. Okay, so that's the disjointness thing there. So let's let S1 be the sum of I going from 1 to SI, maybe I better make that a K, the sum of the ends up to I. Okay? So S1 is N1, S2 is N1 plus N2, S3 is N1 plus N2 plus N3, and so on. Okay? If any of the SI is divisible by 25, then let B be the things in that set, you know, the N1 through N sub I. Okay? If not, then we have 25 numbers with 25 remainders when divided by 25, and those remainders are 1, they're not R, range from 1 to 24. Thus, we got 25 numbers and 24 possibilities, right? Thus, 2 of the S sub I share a common remainder. Okay? So let's name them. Let's call them something. How about, I've already used K for something. How about S and T be natural numbers? Yeah, I don't really want natural numbers. I need something 1 through 25. Sorry. And I'll let S be less than T. Such that, I'm sorry, I didn't even say what they're supposed to do. Such that sorry, I'm having a rough time with this one. S, that's not good, and ST have a common remainder R. That means I can write SS as 25, I don't know, times, how about A and B plus R, and ST is 25 times B plus R for some AB natural numbers. That's what I was thinking about before. Of course, A would have to be less than B. Okay? Then if I subtract S of t minus S sub S, I get 25b plus r minus 25a plus r. The r's cancel, and I'm left with 25. I can group then b minus a. Since b minus a is a natural number, then this is a multiple of 25, and we let b equal, I start at s plus 1, and I go up to n sub t. Okay? For C, do the same thing with a sub 2. And there you go. Sorry for all the scribbling on that one. Okay. Excuse me. 11 says give a proof or counterexample of the following statement. Any set A of 9 whole numbers contains a non-empty set B such that the sum of the elements of B is a multiple of 10. That is not true. Here's my counterexample, and there are many. But I'm going to kind of go on the fact that as long as I keep a 1 in that 1's position, I can't pull out a subset that would be whose sum would be a multiple of 10. So something like 1, 11, 21, 31, 41, 51, 61, 71, I think that's 8, 81. Okay. And there are many ways to do that. In fact, you don't even have to use 1. You could use something like 3, where as long as you keep doing multiples of it 9 times, you don't encounter a 0 in the 1's digit, right? And that takes care of that. 12 says show that any set of 36 whole numbers contains 8 non-empty disjoint subsets B1 through B8, with the sum of the elements of bk being a multiple of k for each k 1 through 8. Well, basically the stunt we just used for 25 would work for n, right? We could always do that stunt. So really, and since these have to be disjoint, the key here is to go ahead and break the set up into disjoint subsets of these lengths, right, and then of length k, 1 through 8. And you'll notice that if you add up 1 through 8, you get 9 times 8 divided by 2. 72 divided by 2 is 36. So our proof for this is to let A1 be N1, A2 be N2, N3, A3 be in 4, 5, 6, A4 be in 7 through N10, A5 be N11 through N15, A6 be N16 through N21, A7 be be N22 through N28, and A sub 8 be N29 through N36, where A is N1 through N36. So these are disjoint. Okay, they're of length K for the subscript, K, and we can pull the stunt that we pulled every time. In fact, we don't even have to do anything. The first one, the element in 1 is trivially a multiple of 1, and can use our sums trick from problem 10, okay, 7 more times to get subsets B2 through B8. Now, that's close enough on this one. Okay, that was the real trick, is that we could partition things out, and then we can do the sums. If you really want to write it out, let S1 be N2, S2 be N3. If neither of those, S2 would be N2 plus N3. If neither of those sums is even, then subtract and get that one. But yeah, it's a nice little trick that we can always use. All right, that's the homework. Good luck studying on the test. See you Monday morning, and we will wrap up our semester. See ya.